Early morning, July 16, 1945, San Francisco Harbor. While the mushroom cloud from the Trinity test still rises over New Mexico's desert 2,000 miles away, the heavy cruiser USS Indianapolis slips quietly from her moorings at 08:36 hours. Deep in her hold, secured in a lead-lined container and guarded by armed Marines, sits the most extraordinary cargo in naval history. Inside that cylinder, 64 kilograms of uranium-235, the entire weapons-grade uranium stockpile of the United States. 3 years of separation work, $2 billion in 1945 money. Atom by painstaking atom, extracted from natural uranium at Oak Ridge, Tennessee. Here's the shocking part. The weapon design using this irreplaceable material had never been tested, not once. In 3 weeks, Captain William Parsons would arm it mid-flight over the Pacific, insert the final explosive charges into a gun barrel while the Enola Gay bounced through turbulence at 30,000 feet, and bet everything on physics calculations scribbled in Los Alamos notebooks. How did Manhattan Project engineers develop such confidence in an untested design that they were willing to use it in combat? The answer reveals one of the most audacious engineering gambles in military history. To understand this story, we need to go back to 1942, when the Manhattan Project faced what seemed like an unsolvable equation. J. Robert Oppenheimer's team at Los Alamos had a simple mission: design a working atomic bomb before Nazi Germany did. But they faced a nightmare scenario that kept military planners awake at night. The physics was straightforward. Take 2 pieces of uranium-235, each below critical mass, smash them together fast enough, and you'd trigger an exponential chain reaction, releasing the energy equivalent of 15,000 tons of TNT. Simple, right? Wrong. Because uranium-235 doesn't exist in nature as a pure element. Natural uranium is 99.3% uranium-238, with only 0.7% of the U-235 isotope needed for weapons. The 2 isotopes are chemically identical. Separating them is like sorting identical twins by weight alone, except you're doing it with atoms. Oak Ridge's massive K-25 gaseous diffusion plant became the solution. This facility, covering 44 acres under one roof, pumped uranium hexafluoride gas through thousands of porous barriers. The slightly lighter U-235 atoms diffused through microscopically faster than U-238. After thousands of passes through these barriers, the enrichment slowly climbed from 0.7% to weapons-grade material. The Y-12 Calitron facility took K-25's partially enriched uranium and pushed it further using electromagnetic separation, achieving enrichment levels around 89% for some batches. Other material was enriched to only 50%. Combined together, Little Boy's uranium averaged about 80% enrichment. The cost was staggering. K-25 consumed as much electricity as a medium-sized city. The electromagnetic calitrons at Y-12 used coils wound with 14,700 tons of silver borrowed from the U.S. Treasury because copper was too scarce. The process was so painfully slow that by early 1945, Oak Ridge had produced only enough enriched uranium for one bomb, one single weapon. There would be no practice shots, no test detonations, no margin for error. But the uranium shortage wasn't even the biggest problem facing Francis Birch's gun-type bomb design team. Initially, Manhattan Project engineers planned to build 2 types of gun-type bombs, one using uranium-235 and another using plutonium-239 produced in Hanford's nuclear reactors. The plutonium bomb, codenamed Thin Man, would be the main weapon. Plutonium could be manufactured in reactors much faster than uranium could be enriched. The strategy made perfect sense.
until April 1944, when disaster struck. Emilio Segre's team at Los Alamos discovered that reactor-bred plutonium contained an unexpected contaminant, plutonium-240. This isotope had a spontaneous fission rate 40,000 times higher than plutonium-239. Every few milliseconds, a Pu-240 nucleus would spontaneously split, spraying neutrons through the surrounding material. What does this mean in practical terms? Imagine trying to bring two pieces of plutonium together in a gun barrel. The projectile fires, accelerating down the barrel. But here's the problem. The two masses must travel several feet before making contact. During those crucial milliseconds of travel time, spontaneous neutrons from Pu-240 would trigger a premature chain reaction before the masses fully assembled. The result? A fizzle. Instead of a 20 kiloton explosion, you'd get maybe 1 kiloton, scattering expensive plutonium across the landscape while accomplishing nothing militarily. Months of reactor operation wasted, the invasion of Japan would proceed without atomic support. American casualties would mount into the hundreds of thousands. The plutonium gun-type design was dead. Thin Man was abandoned in July 1944, forcing the project to pivot entirely to the untested implosion method, which would eventually become Fat Man. That design required surrounding a plutonium core with precision-shaped explosive lenses that compressed the core to criticality in microseconds, faster than spontaneous fission could cause pre-detonation. But what about uranium? Could the gun-type design work with U-235?
Norman Ramsey's calculations gave the team reason for cautious optimism. Uranium-235 had a dramatically lower spontaneous fission rate than plutonium. The neutron background in enriched uranium came primarily from two sources: trace amounts of uranium-234 and residual uranium-238 in the enriched material. The math worked out like this. Little Boy's 64 kilograms of uranium, enriched to an average of 80% U-235, produced approximately 1 spontaneous fission every 14 milliseconds. This gave engineers a critical window of time. As long as they could assemble the critical mass in less than 14 milliseconds, pre-detonation probability remained acceptably low, less than 1% chance of fizzle. Here's where the engineering elegance emerged. The gun-type design could achieve assembly speeds that the plutonium bomb could never match, specifically because uranium's lower neutron background made slower assembly acceptable. Francis Birch's team designed a weapon that was essentially an artillery piece sealed inside a bomb. A 6-foot gun barrel ran through the center of the bomb. At the breech end sat a uranium projectile shaped like a hollow cylinder, weighing approximately 38.5 kilograms based on declassified estimates. This projectile surrounded 4 silk bags filled with cordite powder, the same propellant used in naval guns. At the muzzle end, secured inside a target assembly surrounded by tungsten carbide tamper blocks, sat the target, approximately 25.5 kilograms of solid uranium-shaped spike, 7 inches long and 4 inches in diameter. When conventional explosives ignited the cordite charges, the uranium projectile would accelerate down the barrel at approximately 1,000 feet per second. The hollow projectile would slam over the spike target, joining the two subcritical masses into a supercritical configuration in about 10 milliseconds. 10 milliseconds. Faster than the spontaneous neutron background. Faster than pre-detonation could occur. Fast enough to work. But working in theory and working in practice are two very different things.
This is where the Manhattan Project's engineering methodology becomes fascinating. They couldn't test the complete weapon, but they could validate every single component and subsystem individually. At Los Alamos, engineers constructed exact-scale mock-ups of the gun mechanism.
They test-fired the cordite charges hundreds of times using non-fissile projectiles, measuring muzzle velocities and acceleration curves. They verified that a uranium projectile machined to tolerances of thousandths of an inch would survive the acceleration forces without deforming or fragmenting. They built test assemblies using non-enriched uranium and measured how precisely the projectile fit over the target spike. The cylindrical projectile had to slide over the target with perfect alignment. Any wobble or misalignment could cause the assembly to jam part-way, creating a subcritical geometry that would fizzle or fail to detonate at all. Metallurgists tested uranium's behavior under explosive acceleration. Unlike steel or aluminum, uranium is dense, brittle, and behaves unpredictably under shock loading. Would the projectile crack from acceleration stresses? Would the target spike shatter on impact? Extensive materials testing provided confidence that solid uranium components would remain intact throughout the assembly process. Norman Ramsey's team conducted elaborate neutron diffusion calculations using mechanical calculators and slide rules. They modeled the neutron multiplication factor at every stage of assembly. Their calculations showed that once the projectile began sliding over the target spike, criticality would be achieved when approximately 60% of the insertion was complete. At that moment, the exponential chain reaction would begin. The critical calculation? From the moment criticality was achieved to complete disassembly of the core from explosive energy would take less than 1 microsecond. During that microsecond, approximately 1.38% of the uranium would undergo fission. That's less than 1 kilogram of material actually splitting atoms. But thanks to Einstein's equation E equals mc squared, that tiny amount of mass would convert to 63 trillion joules of energy, equivalent to 15,000 tons of TNT. Every component was tested. Every calculation was verified through independent methods by different teams. Every possible failure mode was analyzed and mitigated. Physicists at Los Alamos even calculated the pre-detonation probability down to decimal points, confirming it remained below acceptable risk thresholds. But still, they had never assembled all the pieces together with enriched uranium and detonated it. What they had instead was overwhelming theoretical confidence backed by exhaustive component validation.
Why didn't they test Little Boy like they tested the plutonium implosion design at Trinity? The answer came down to cold mathematics and resource constraints. The Trinity test on July 16, 1945, the same day the USS Indianapolis departed San Francisco, consumed the entire available plutonium stockpile. But Hanford's reactors could produce more plutonium relatively quickly. By early August, enough plutonium existed for the Fat Man bomb dropped on Nagasaki. Uranium was different. K-25 and the Y-12 Calitron facility at Oak Ridge produced enriched uranium at agonizingly slow rates. The entire Oak Ridge complex, operating at maximum capacity, generated roughly 1 kilogram of weapons-grade uranium per day by mid-1945. It had taken from 1943 to July 1945 more than 2 years to accumulate the 64 kilograms needed for Little Boy. Military planners faced an impossible choice: test the design and delay the uranium bomb's combat use by 2 to 3 months while Oak Ridge enriched another batch, or trust the engineering and potentially waste the only atomic weapon available if it failed. General Leslie Groves and the scientific leadership reviewed the evidence. The component tests were flawless. The physics calculations from multiple independent teams all agreed within narrow margins. The design was so mechanically straightforward that failure modes were difficult to even imagine. A gun fires a projectile. The projectile hits a target. Supercriticality occurs. The bomb explodes.
compared to Fat Man's nightmarishly complex implosion system requiring 32 explosive lenses to detonate within microseconds of each other in perfect symmetry. Little Boy was practically foolproof. The gun-type mechanism used technology perfected over centuries of artillery development. The decision was made. Little Boy would go to war untested.
This brings us to the most dramatic moment in the story. August 6, 1945. The Enola Gay sits on Tinian's North Field runway, engines warming. At approximately 0230 hours, while the crew conducts final pre-flight checks, Captain William Deke Parsons climbs into the bomb bay. Parsons had insisted on this dangerous procedure after witnessing 4 B-29s crash on takeoff from Tinian's runways during the previous weeks. The heavily loaded superfortresses, struggling with tropical heat and maximum fuel loads, had a disturbing tendency to lose power on takeoff and cartwheel into the Pacific just beyond the runway. The idea of a fully armed atomic bomb aboard a crashing aircraft terrified Parsons. A conventional explosion from the impact might not trigger nuclear fission. The cordite charges required precise electrical ignition, but it would scatter 64 kilograms of irreplaceable weapons-grade uranium across Tinian Island, contaminating the airfield and ending the atomic bombing campaign before it began. His solution? Arm the bomb in flight after takeoff. Once the Enola Gay reached safe altitude over the Pacific, Parsons would remove the bomb's rear plate, insert the cordite powder bags into the breech, secure the projectile in place, connect the firing circuits, and replace the armor plate. It sounds simple. It wasn't. At 0245 hours, the Enola Gay thundered down runway Able and lifted safely into the darkness. 30 minutes later, as the aircraft climbed through 5,000 feet over the Pacific, Parsons began the most critical task of the mission. Working by flashlight in the cramped, freezing bomb bay, the unpressurized space exposed to -20-degree temperatures at altitude, Parsons removed 3 armor plates secured by dozens of bolts. He carefully inserted the 4 silk bags of cordite powder, ensuring no tears or contamination. Each bag had to be positioned precisely to ensure uniform burning and consistent projectile acceleration. Then came the firing circuit, a nest of wires that had to be attached in precisely the correct sequence. One mistake, one wrong connection, one accidental discharge of static electricity, and the bomb would detonate immediately, vaporizing the Enola Gay and its crew in a millisecond of nuclear fire over the Pacific. Parsons worked methodically, his hands steady despite the cold and turbulence, checking each step against the procedures he had rehearsed dozens of times in the workshops at Tinian. His assistant, Second Lieutenant Morris Jepson, stood ready with tools and double-checked every connection. The work took longer than planned. The bomb bay was cramped, the aircraft bounced through tropical air currents, and the importance of absolute precision slowed every movement. But Parsons was nothing if not thorough. Finally, as the Enola Gay droned westward toward Japan, Parsons tightened the last bolt and reconnected the final wire. Little Boy was armed. The untested weapon was now fully operational, carrying the hopes of ending history's bloodiest war.
At 8:15 hours Hiroshima time, Bombardier Thomas Farabee released Little Boy from 31,060 feet above the city. For 43 seconds, the weapon fell through the summer air, its barometric triggers monitoring altitude with precision clockwork mechanisms. At 1,968 feet above Hiroshima, the electrical firing signal traveled to the cordite charges. The propellant ignited in a fraction of a second, accelerating the hollow uranium projectile down the 6-foot barrel. In 10 milliseconds, exactly as calculated, the projectile slammed over the target spike.
The two subcritical masses became one supercritical assembly. Criticality was achieved. The exponential chain reaction began. 1 microsecond later, less than 1 kilogram of uranium had undergone fission, but that was enough. The explosion released 15 kilotons of energy, exactly within the range that Los Alamos calculations had predicted. The yield matched theoretical models to within 20%, remarkable accuracy for an untested weapon based entirely on paper calculations and component testing. The untested design worked perfectly. But the story of Little Boy reveals something profound about engineering confidence and calculated risk. The Manhattan Project team didn't succeed because they were reckless. They succeeded because they were systematically thorough. They tested what could be tested. They calculated what could be calculated. They validated every component, every subsystem, every assumption. When testing wasn't possible, they built redundancy into their verification methods. Multiple teams performed independent calculations using different mathematical approaches. Different experimental methods confirmed the same physical constants. Every prediction was checked and double-checked. Modern nuclear weapons development never repeats this approach. Today's designs undergo exhaustive computer simulations running on supercomputers that can model nuclear physics down to individual neutron interactions. The Comprehensive Nuclear Test Treaty has made full-scale testing politically unacceptable for most nations. But the engineering principles that gave Manhattan Project scientists confidence in Little Boy remain relevant across all fields of engineering. Understand your failure modes completely. Test every component to destruction. Calculate from first principles and verify through multiple independent methods. Build systems simple enough that their operation can be predicted with confidence. When you cannot afford failure, make failure theoretically impossible through systematic elimination of every uncertainty.
The story of Little Boy demonstrates something crucial about engineering under extreme constraints. When you cannot afford failure and testing isn't possible, systematic validation becomes paramount. This approach applies far beyond weapons development. SpaceX uses similar philosophy when launching missions to Mars, where real-time intervention is impossible. You cannot fix a spacecraft 200 million miles away. Every system must work perfectly the first time. The solution? Exhaustive component testing, redundant verification methods, and multiple independent calculation pathways, exactly the approach Los Alamos used for Little Boy. Medical device engineers employ the same methodology when designing implantable pacemakers or artificial heart valves. You get one chance. The device must function flawlessly for years inside a human body with no maintenance possible. How do you achieve that confidence? Component testing, accelerated life testing, failure mode analysis, and mathematical modeling. The Manhattan Project playbook applied to saving lives instead of ending them. Any field where failure is unacceptable and do-overs aren't possible borrows from this systematic approach. Submarine design, deep-sea oil platforms, commercial aircraft, nuclear power plants, bridge engineering. When human lives depend on systems working correctly the first time, engineers fall back on the principles perfected at Los Alamos in 1945. The engineers who built Little Boy weren't gambling recklessly with an untested weapon. They were calculating risk with unprecedented rigor, building confidence through systematic validation, and accepting operational deployment only after eliminating every reducible uncertainty. That's the lesson. When you can't test the complete system, you test everything else until failure becomes theoretically impossible. If this deep dive into technical problem solving in military history intrigued you, subscribe for more stories about engineering brilliance under pressure.
Next episode, we explore how British engineers built the bouncing bomb that destroyed Germany's dams and the hydrodynamics calculations that made it work without modern computers. Hit that subscribe button to see how creative minds solve impossible problems when the stakes couldn't be higher.